This video is the second of two videos covering real analysis, logic, and proofs. In our first video, we talked about logical statements and connectors, logical implications, the truth table, and the tautology. In this video, we are going to start with quantifiers and then look at how to negate quantifiers. There are a number of examples, and at the end of the video, I have two problems for you to do by way of review. One thing I did want to review before going to our new material is the negation of the and, the negation of the or, and the negation of the implication. So when you negate the and, you have the negative p, the negative q, but the and becomes an or. Similarly, when you negate the or, you have the negation of the p, the negation of the q, but the or becomes an and. Last, when you negate an implication, so the only time that an implication is false is when you have p is true and you have not q. So the negation of the implication is p and not q. Now we are ready to go on and talk about quantifiers. So there are two quantifiers. The first one is the universal quantifier, and that is for all x, p of x is true. In other words, we would write this for all x, p of x. The existential quantifier is there exists an x such that p of x is true, and the shorthand is this backwards e, there exists x such that p of x. So quantifiers take statements with a variable. In other words, we have this variable x, and usually these statements cannot be evaluated as true or false, but then the quantifier will make them into propositions which can be evaluated as true or false, and we'll do an example. But also note, we can also plug in a value for the variable to determine if it's true or false. Also the last note, we often use quantifiers in proofs. So the example, x squared minus 5x plus 6 equals 0. So we had looked at this before, and we said it was not a logical statement because we cannot evaluate it as true or false. But the first way we can evaluate this as true or false is if we plug in a value for the variable. So we can decide if x is equal to 2, we can decide that this statement is probably false, but I'm not going to actually do the arithmetic. Or the other thing we can do, so to note, p of x technically, x squared minus 5x plus 6 equals 0, is called an open statement. And an open statement is a statement that involves a variable. In other words, x is our variable, and cannot be evaluated as true or false as it is. But if you can evaluate it as true or false if either you plug in a variable or you use a quantifier. So we'll look at the universal quantifier for all x p of x. In other words, if we said for all x, x squared minus 5x plus 6x is equal to 0. So this would be a false statement, right? If x is, just say, even any real number. We could use also the quantifier there exists an x p of x such that x squared minus 5x plus 6 equals 0. And if we did our algebra, we could determine if there probably is one. Yeah, 3 and 2, right? This factors into 3 and 2. So this is a true statement because there exists one. You only have to find one. A couple of other notes. Sometimes there's this backwards epsilon, so you say there exists x such that this backwards epsilon, which I don't like to use because it looks a lot like there exists. But this means such that, the same thing as my st, such that. And you will notice that whenever you have a for all, it's just a statement, for all x p of x. Sometimes you put a comma, for all x p of x. For the exists, you usually say such that. Here's some examples for you to pause the video and give a quick try to write these statements as with universal quantifiers. And here are my solutions. There exists x such that x is less than 7. There's a positive number such that x squared is equal to 5. So there exists x such that x is positive and x squared is equal to 5. Or I could have done there exists x greater than 0 such that. This little epsilon that's backwards is such that. I don't like this epsilon backwards because it looks too much like there exists. But I would rather put st. But anyway, here, the backwards epsilon is such that. For every positive integer m, there is a positive number n, such that n is less than 1 over m. So for every positive integer m, so for all m greater than 0 because it's positive, there exists a positive number n. So there exists n that's greater than 0, such that n is less than 1 over m. If n is greater than capital N, then f of x with the subscript n minus f of x is less than or equal to 3 for all x in A. So for all n greater than this capital N, then for all x in A, we have this condition here. No positive number x satisfies the equation f of x is equal to 5. So for all x greater than 0, f of x is not equal to 5. This one's kind of tricky because it's a for all. Even though it says no positive integer satisfies it, it means for all integers, this statement is false. The next thing we want to do is look at the negation of quantifiers. So the negation of a for all is there exists, something that is not p of x. And the negation of a there exists p of x means that for all x, not p of x. So I'm going to take a minute to tell you, just give you a note. So if you think about it, the negation of everything is good, and everything is good would look like for all x, p of x is good. But the negation of this statement is not that everything is bad. The negation, according to these rules over here, is that there exists x such that not p of x. In other words, there exists x such that x is bad. You only have to have one. It isn't that everything has to be bad. So the negation, you don't want to think of it as like the polar opposite where it negates it just means just enough to make this statement negative. So what's just enough to make for all x everything is good? All you have to do to disprove this statement is find one thing that is bad. So here I have another example. You want to take a look and negate each of these statements. And like the other example, it is possible that you can do these intuitively, but it's very important when things become more difficult that you're able to do these formally. So I would highly encourage you to write this as a statement with p of x and ands and implications, and then go through and use the rules for negation of these quantifiers, and then be able to write it back in English. But again, it's very important you're able to do it formally. Even if you can see obviously what it is intuitively, it will behoove you to do the formal steps. Remember when you... So the first solution, for every x in A, f of x is greater than 5. So I wrote that here. For all x, f of x is greater than 5. And I want to negate that. And using my negation rule, all I need to do is find one x. There exists some x such that the negative isn't true. In other words, f of x is less than or equal to 5. So here's my negation. There exists x such that f of x is less than or equal to 5. The next problem is to negate there exists a positive number y such that g of y is between 0 and 1. So I wrote this again. So there exists a positive number, so there exists y greater than 0 such that g of y is between 0 and 1. And now to negate a there exists, and I have that note over here, and again this is the such that, it looks like a there exists, so I don't really like it, but here it is. To negate the there exists x such that p of x, you take the for all x and then the not p of x. So I'm going to take for all y greater than 0, and then I'm going to negate the rest, which is g of y is between 0 and 1. And g of y between 0 and 1 is really two conditions, that g of y is greater than 0 and g of y is less than or equal to 1. So when I take the negation, I'm going to have 0 is greater than or equal to g of y. Actually, this should just be greater than. Or, remember when you distribute the negation, you have to change the ands to ors, and you'll have g of x is greater than 1. The next problem is this here. For all x and y, there exists z and b such that x plus y is equal to z. So I rewrote this symbolically: for all x, for all y, there exists z in B such that x plus y is equal to z. So you can see it's a direct translation. And I want to negate this. Now to negate the for all, I need to replace it with there exists x such that. So I'm going to say there exists x, there exists y such that, and now to negate my there exists, I have to write for all. So for all z in B, I have x plus y, and now I need to negate this portion is not equal to z. So this is my complete negation here. This last problem here is a little bit trickier, so I did it in parts. I started over here, but let's just read through it. For all epsilon greater than 0, there exists capital N such that for all little n, if little n is greater than or equal to capital N, then for all x and s, fn of x minus f of x, the absolute value, is less than epsilon. So I chose this one because it's very hard to get an intuition for this, so you have to go by the rules. So I have this rewritten here one more time, and I have the negation in front, and that's equivalent to, and what I decided to do is kind of do this in little pieces. First I negate all these quantifiers. So the for alls become there exists such that, the there exists become for all, and then I have for all n, so there's another there exists n such that, and then the rest of it I negated. So on the next line I have all my quantifiers, and I'm going to start negating this portion here, and it's the implication that I'm negating. I have an if, something, and then a then. So if you recall, to negate an implication, you take the antecedent, so that's n greater than or equal to capital N, and you AND it with the negation of the consequence. So here I say I want to AND it with the negation of the consequence. And finally, I brought everything down. I have my quantifiers, my antecedent, and ANDed, and then to negate the consequent, I take my for alls, change it to there exists x such that, there exists x in S such that, and then I negate this portion here. Fn of x minus f of x, absolute value, is greater than now, or equal to epsilon. And now I am finished. For my last example, I have this expression here. For all x, there exists y, such that p of xy and q of xy implies r of xy. And the problem is to negate and simplify. And here is my solution. I considered x minus y less than 0 to be my p of xy, and my q of xy is x less than or equal to y. This step isn't really necessary, but I did it because I just didn't want to carry all this around. I wanted to make it a shorter statement. So I translated my for all x, for all y to p of x, which is x minus y is less than 0, implies q of xy, which is x is less than or equal to y. But then I negate this because that was my task. And remember, when you negate for alls, those become there exists, and then you negate what's inside. And to negate the implication, you take the antecedent, and then you AND it with the negation of the consequent. So this is my negation. But I really should finish it off by translating my p of xy and my q of xy back to my original. So I have there exists x, there exists y, p of xy, which is x minus y is less than 0, and the negation of q of xy will be x is greater than y. So this here is the negation of my statement. For review, I have these 5 problems, but you've already done the first 2 in part 1, so you only need to do the last 3. Go ahead and pause the video, give them a try, and on the next slide I will have solutions. Here are the solutions. And that is it for this video. Thank you for watching.